In section 8.4, we talk about binomial distributions. This is the first part. Let's go over what makes an experiment a binomial distribution versus the probability distributions we saw back in chapter 7. So an experiment that has only two outcomes are called binomial experiments, also known as Bernoulli trials. One outcome is considered to be a success, the other a failure. We've already talked about several different experiments that can be considered as a binomial experiment. So when you think about the coin tossing, a success might be getting a head and a failure might be getting the tail. The number of children in an n-child family. So success would be having a girl and failure would be having a boy, or vice versa. Defective versus not defective, picking parts out of a sample, or also a true false quiz. Those are all examples of where there are only two outcomes, one which would be a success and the other a failure. A binomial experiment has the following properties. So the number of trials is fixed. So you're going to toss the coin 5 times. You're going to have a 3-child family. The true false quiz only has 6 questions on it. There are only 2 outcomes of each trial, the success or the failure. The probability of success in each trial is the same. So the probability of having a girl as the first child and the girl as the second child, and the girl as the third child are all the same. And then finally, the trials are independent of each other. What you have as your first child does not influence what you have as your second child. So the first example wants us to simply determine whether or not each of the outcomes or each of the experiments is a binomial experiment. So the first example, part A, says rolling a fair die 5 times and observing the number of times a 1 is thrown. Well, in this example, we could consider a success to be rolling a 1. Anything else would be a failure. So yes, this is an example of a binomial distribution. What part B says, rolling a fair die 5 times and observing the number that appears most. Well, it is a fixed number of trials, but because you're recording the actual number as a 1 or a 2 or a 3 or a 4 or 5 or a 6, those are 6 outcomes, not just 2 outcomes. That is not a binomial experiment. Part C says, consider 10 people browsing in a store and observing if they make a purchase. Well, we've got a fixed number of trials. If we let the success of making a purchase be the success and failure making not a purchase, then yes, it would be a binomial experiment. We are assuming in this one that the probability of me purchasing and you purchasing are equal. And finally, part D says, recording the number of hits a baseball player whose batting average is .325 gets after being up to bat 5 times. So you're either going to hit the ball or you're not. The probability of the batting average would be your probability of success. So definitely a binomial experiment. So if you can classify the experiment as a binomial, then we actually have a formula that we can use. So in a binomial experiment in which the probability of success is in any trial is P. So P stands for the probability of a success. Sorry. And Q then is the probability of a failure or the complement. Probability of no success, which sounds so much friendlier than failure. It is important to note that P plus Q is equal to 1 because, again, there are only 2 outcomes. So, and we have the probability of exactly X successes in N trials is given by C, and then we have N comma X. So this is the combination of N items taken X at a time. So total number of trials. And this is the number of outcomes. So number of successes that you want, basically, times P to the X power times Q to the N minus X power. So it's an ugly looking formula, but luckily there's some things that help it make sense in your brain. The P and the Q together have to add to 1. This is the probability that you get the 3 successes out of the 5 trials. This one over here is the probability of getting the failure on the other 2 trials. So together these 2 exponents should add to N. So let's just get a practice using the calculator and working through one of them. So example 2 starts off with, use the formula and find for the given value. So if the total number of trials is 4, and we're looking for 1 successful outcome, and the probability of a successful outcome is 1 out of 3. So you might be tossing a loaded die, and what you're after is a success is rolling a 1, and the probability of getting a 1 is a 1/3. We want 1 out of 4 trials. So that probability would be the combination of 4, choose 1, bigger number always first when you do a combination, times, now we're going to take P, which is 1/3. We're going to raise it to the X power, which is 1. Then we'll multiply that by its complement, which would be 2/3, and we'll do 4 minus 1 as the exponent. Normally, I'll just subtract that automatically. I won't write it out. So that's going to give us the combination of 4, choose 1, which is 4, times 1/3 to the first power times 2/3 to the third power. And if you multiply that out on your calculator, you're going to get a nice decimal of 0.395. So the probability of getting one successful outcome amongst 4 trials, when the probability of an individual outcome being successful is 1/3, is 0.395. Part B on that problem, same kind of idea. We're going to let n equal 5. X this time is going to be equal to 3. And the probability of a success this time is 0.2. So n is 5, x is 3, and the probability of success is 0.2. So that would be the combination of 5, choose 3, times the 0.2, that's the probability of a success raised to the smaller number, which is 3. And then we're going to multiply that by 0.8, its complement. So again, these two have to add to 1. So to find Q, I just take 1 minus the 0.2. And to find the exponent on this, I'm just going to take the difference between the 5 and the 3, which is 2. So again, the base numbers have to add to 1. The two exponents have to add to n. And number crunching that through the calculator should give you 0.0512.